So next talk is Julien Morin from University of Montpellier. And this is the last talk on the magnetic star.
Hello everyone. So indeed, I'm going to speak about magnetic cycles of M dwarfs with SPIRou, and this can give you both an idea of what we've been able to do in the past few years in the framework of the SPIRou large programs, but also what we will be able to do in a larger fashion with the Weno-KAO and in the framework of the future Amaki community survey. So the results I'm going to highlight have mainly been produced by a few young researchers whose name I underline here. So Stefano Bellotti, Manon Diez, and Lisa Lehmann. So to start with, I wanted just to show, to remind a few things about magnetic cycles and especially magnetic cycles of M dwarfs. So the fact that the global magnetic field of the sun undergoes cycles is a very striking feature of the dynamo-generated solar magnetic field, and that's now something that we start to be able to study on significant sample of solar type stars. For instance, you can see here on the right side the variation of the calcium activity index of the K dwarf 61 Sig A along several activity cycles. And thanks to spectral parameters, we are even able to link these activity cycles to proper magnetic cycles with regular polarity reversals. And that's what you can see on the bottom figure with two different states of the large-scale magnetic field of the same star. And these are magnetic maps which have been reconstructed from spectral parametric observation collected with Narval at TBL. So now the question is, what about M dwarfs? Because so far, at least before the SLS, before SPIRou came online, we had no direct detection of magnetic cycles on M dwarfs, but there were hints of chromospheric activity cycles, of radio polarization changes, also of photometric activity cycles. And so the idea is to try now to really go and find directly regular polarity reversals that we can link back to these activity cycles. Also, another issue about stellar dynamos is that when we carried out the first survey of spectroparametric survey of M dwarfs with ESPaDOnS a few years ago, we found that the low mass rapidly rotating stars. So here in this plot on the right, you can see all the stars that we had studied, and in a mass period diagram. So you can see that in this in this bottom left corner, so this low mass rapidly rotating stars, we see that there are two different types of magnetic topologies, whereas the stars share very similar parameters. And then an idea was that was developed in the early 2010s was the idea of dynamo bistability. But an alternate explanation would be the existence of long cycles. So that will be also an additional interest. And of course, in the exoplanet context, as you know, it's important to understand the space weather environment in which the planets evolve. And obviously, better understanding magnetic cycles of M dwarfs is crucial. So that's basically the context of these studies. Now I will show the results first of two types of studies. So the first one is about active M dwarfs. So we've been selected 4 of these stars, which we had already studied back in 2006-2008. The names are given here. So some of them, you heard them already in the previous talks, like AD-LEO or EV-Lac. And for these stars, basically, which span the whole M-type mass range, we have observation which spread over 15 years. So we don't have a full coverage each year, but we have observations spread over this baseline. Here is the first interesting example of the results obtained by Stefano Bellotti. I show on the top the longitudinal magnetic field measurements obtained each year, and you can see that with SPIRou already on the right side we have much denser time series which are pretty interesting, as you will see afterwards. And also we can see that there is obviously an evolution on the mean magnetic field that we measure each year, and also on the dispersion of the measurements. Under the bottom figure you see the same measurements but only restricted to the most recent ones, so post 2019, which are phase folded, and you see that indeed there is clearly a change in the surface magnetic field. when you go to the Doppler imaging modeling of this star, of this data set, what you can see is that indeed, on the left, we start with a perfectly aligned dipole, and as we go to 2019, 2020, the dipole is tilting, and actually more recent observation show that the dipole comes back to an actual dipole, and so that we had a dipole exertion, or what we can call also a fade reversal. And what we see is that here, it was crucial really to obtain observations each year, so it's really important to come back regularly to the same star. Although before we thought that the magnetics of M dwarfs did evolve only slowly, it seems now that there is a possibility for very fast evolution, so that it's really important to observe them each year. So this was about an example about active M dwarfs, and we have obtained also interesting results on the other stars, showing that they significantly evolve on a time scale of a few years. And now I will move to the slowly rotating M dwarfs. So the slowly rotating M dwarfs are particularly interesting because it has become possible to study them with the advent of SPIRou. Before it was not possible. ESPaDOnS was not sensitive enough to do that. And what you can see here on the right plot is the classical rotation magnetic field relation. So you have basically the average magnetic field reconstructed from spectroperimetric observation as a function of the Rossby number, which is a dimensionless version of the rotation period. So as the stars rotate faster, first the magnetic field intensity increases until it saturates on the plateau. And what you see in red are these stars, these slowly rotating stars, slowly rotating M dwarfs that we have studied with SPIRou, but which show a surprisingly strong magnetic field. So this was really a surprise. It was already evidenced by the studies by Pascal Fouquet and Jean-François Donati in 2023. And later on, Lisa Lehmann studied a small sample of 6 of these stars. And what she has shown in particular is that several of these stars show significant evolution of the large-scale magnetic field over short periods. Again, you have to reobserve the star each year to be able to capture that. And here is a most striking example of the J1151, for which we see for the first time a reversal of the large-scale magnetic field of an M dwarf. And obviously, we need to continue observing to observe the star to see if we can really observe a full magnetic cycle. So these were about the results that we have obtained so far with SPIRou, and especially in the framework of the SPIRou large programs. And now, what's next? As was said before, especially in the Amaki community survey presentation, we want to take advantage of Plato for our observation, for our spectroperimetric observations. And Plato, as you know, will have the double aim of discovering exoplanets and performing asteroseismology. In our context of magnetic cycles, Plato will be very useful to actually give us additional information on the stars. And what we have done so far, so it's to engage in a long-term monitoring of selected M dwarfs in the Plato southern field. So we selected the stars from Gaia DR3 data. We used the Tesla curves to ensure that we had the proper rotation period and optimize our observing strategy, and also to determine what are the parameters of the stars. And we also checked nearby contaminants from ImageJet to select really the best stars from which we are sure that we can have really interesting light curves. So we started to monitor 6,000 M dwarfs in 24B. And here I highlight these stars plus a few other stars that we have started to observe in a mass period diagram. And you can see also as transparent dots additional stars that we are considering to add to our sample, in particular northern targets, which will complement this sample of Plato southern targets to help us provide context on how the magnetic cycle properties depend on the stellar properties. As you can see, most of these targets, because they were selected to be observable in short exposure times with SPIRou, they are early M dwarfs, and as such, they make excellent Wenao-KO targets because it is a sort of sweet spot where you can have relevant spectroperimetric information from both the optical and the infrared, and also you can get all the classical activity indicators from ESPaDONS, so it's really, you get really a lot of information on this star. And if you want to have more information on this survey, on the first results of these M dwarfs, I encourage you to have a look at Manondier's poster, if you have not yet done so, to see the first results of the program. And with this, I will thank you for your attention. And also I take the opportunity to thank the CFHT staff for their continuous support over the years, which made all these programs possible. Thank you.
Thank you. Question for Julien.
Thank you for the excellent talk. I just had a question, I guess, in broader scope. Could you comment on, I guess, the comparison between like your slowly rotating dwarfs and what we kind of understand about the rapidly rotating ones? So I guess in terms of like magnetic activity and magnetic structure, how that compares, I guess, the function of like mass or rotation. So I guess where do the two kind of intersect?
Well, so the rapidly rotating dwarfs that we could study before SPIRou, they had rotation periods, so between a fraction of a day and let's say a few days. At most, it was like 15 days. And what we used to observe was that for fully conductive stars, we are strong axial dipoles, and for partly conductive stars, we had weaker non-axis symmetric magnetic field with a bit of toroidal field, let's say. Now, if you go to these slow rotators, so they can have a really long rotation period on several tens of days, even hundreds of days. What we see is that they seem to have simple large-scale magnetic field, but it's also an observational bias because as they rotate very slowly, you have a very low spatial resolution with the DI. And also what we observe really surprisingly is that the field is much stronger than what we expected. So it doesn't match at all with the rotation activity relation that we had for other stars. And this is also for only a subsample. There is a sample of stars which seems to match the relation and the other one not. So it's really surprising.
So thank you, Julien. So we have to move on.
Thank you.